than these 2x and negative 2x, we got 0. When we add them together, we get positive y, and when we add 10 to negative 12, we got negative 2, which is the same result. And here we go, the rest is so easy. So let's take a look at another slide. Therefore, let's talk about elimination method for solving three variable systems. Beforehand, we did two variable systems and explained some alternatives options to solve two variable systems. And right now I'm gonna explain how to do three variable systems step by step. So let's get started. Step one is exactly about choose two equations and eliminate just one variable by multiplying by constants and adding. Step two is totally about being totally choose a different pair of equations and eliminate the same variable. Step three, you now have two equations with two variables. Solve this system using the substitution elimination method. Step 4. Substitute the values of two variables back into one of the original third variable. In summary, it talks about choose two variable, solve it, have one equation, and try to solve with the try to have a method. Which do you want, substitution or elimination? You should have common value with this third equation. So that's all about this. And I restated each steps again after what. So step one is all about solve one equation for one variable. Step two is substitute this expression into the other two equations. Step three is you now have two equations with two variables. Solve this system using the substitution or elimination method, and at the end substitute the values of two variables back into one of the original equations to find the third variable. So that's all. It's so easy. One of the most crucial topics in mathematics is types of solutions in systematic equations. So we have three types: one solution, no solution, and infinitely many solutions. One solution is defined as it intersects at a single point. In no solution, there are parallel lines, so that's why um, they don't intersect. And one reason for this is because they are parallel lines. So let's take a look at each solutions. Here we go, and look at the coefficient here, 1. Here it is, 2. What about y? We have 1, we have here negative 1. And if we um, do it just like this, positive 1, positive 1, okay, positive 1, sorry for the bad plus sign, equals negative 1, and 3 over 1. So here you see that this is 1 over 2, 0 0.5. Here we go. Here we have negative 1 and 3 over 1. And here it is, they're not equal. So that's why we have just one solution of x and y. So let's take a look at no solution example. Here we have x plus y equals 3, x plus y equals 5. Let's sketch a graph for better explanation. Here it is, ordinate and axis. Let's mark, imagine line just like this. Here it is, and here it is. X plus. That's why we have the coefficient here 1, coefficient here 1, coefficient here 1, coefficient here 1. They, if we divide them each other, they are same. But 3 and 5 are different. So that's why they show that 3 and 5, if they their coefficients are the same, but the constants are different. Uh, Here it is. We have parallel lines. So take a look at infinitely many solutions. Infinitely many solutions are exactly just like this. When we sketch a graph, or when we calculate them in decimals or any random graph calculator, we're going to see that they lie on each line. The equations are the same, totally the same. So here's the proof that when we multiply this one of them above, it's, this x, y, 3 are less than 2x, 2y, and 6. We should multiply them by 2. So exactly they are the same. But even though it seems less, they are the same, because the number which is multiple, the number which is the product of anything, it doesn't change anything, because anytime, any other time, we can divide them by 2, and it doesn't matter what you do, and they lie on the same line. And so it doesn't matter if we sketch a graph like this: 6x plus 6y equals 12. This, this, and this, they are always considered as infinitely many solutions. They lie on the same line, and it doesn't change any fact. In conclusion,